Okay, so we'll go ahead and get started. There's kind of an issue with the syllabus in terms of I scheduled 7 lectures for this module, but that's like way too many. Essentially, we'll probably finish today. But given the timing with my other class, they're going to have an exam. I definitely don't want to write 2 exams tomorrow. So most likely, we'll probably finish this module 4 stuff today. If not, it'll go a little bit into Wednesday, but then I would say we'll plan on having your module 4 exam next week sometime, whether it's Monday or Tuesday based on timing. And then for module 5, I think what we'll do is I was originally going to have it just be like synthesis oriented, but we still have quite a few lectures left. So I think I'm just going to revert back to the biomolecules. So we'll circle back to carbohydrates in the sense of they're used as the sugar base for DNA and RNA. And we'll talk about amino acids and peptides and proteins. And I think that will fill up the rest of the semester. And because some of those topics can take a while to talk about, especially when we get into like the sequencing of amino acids, that can be a couple days discussion. So today we'll get as far as we can in terms of the alpha carbon chemistry. So we talked about self and cross aldol products. We'll finish up with the intramolecular cyclization, so intramolecular aldol. And then we'll get into the Claisen reaction, which is essentially we're going up an oxidation state at the beta carbon. And then what are the implications of making beta keto carbonyl compounds? And then we'll see how far we get if, because once we get past that stage, there's a thing we need to revisit in terms of the aldol. So we had seen from last time the condensation of ethanol with propanol, how that's a crossed aldol. So that's where you have the nucleophile and electrophile are 2 separate molecules. But what if they're both within one molecule? And this is called an intramolecular reaction. So that contains, so nucleophile and electrophile are in the same molecule. And that really, a consequence of that is you're going to form a ring. And part of the issue of figuring that out is what size ring are you going to form? And so it's always helpful to number your carbon chains. And as we'll see in the example that's given with this dione, so 2 and 7 indicate the locations of the carbonyls. Where do we form the enolate? Because if you look, the molecule is symmetric. So carbons 1 and 8, 3 and 6 are the same. So there's essentially 2 different alpha carbons. And we've been saying, where do you enolize from? That's going to make a difference in how that enolate then attacks the other carbonyl and what the ring size will be. So I thought we would, so we got 8. I'll look at that. So again, the enolate and the electrophile are within the same molecule. We have alpha and then alpha prime. And so let's just put up a little scenario here where we can predict what would be more reasonable. Say we generate the enolate at the alpha carbon. So we'll say nucleophile, that's carbon 1. Electrophile is then carbon 7. So what that's telling us is ultimately that's going to form a 7-membered ring. What if we did alpha prime? So the nucleophile would be at carbon 3, and the electrophile carbon 7. So that would get us 1, 2, 3, 4, a 5-membered ring. So probably the sweet spot for these are 5 and 6. 7 is unfavored. One eventually the ring size gets, or the chain gets so floppy that it's hard for 1 and 7 to even connect. So a smaller ring size is probably more favored because ultimately those carbons are closer to one another. So 5 and 6 are preferred. When you get outside of those, there's probably other factors involved. But for the time being, let's form the enolate at carbon 3 and then cyclize it onto carbon 7. So let me just put some numbers in here so I myself don't lose count. So there's the enolate. Again, carbon 3 is the nucleophile, carbon 7 is the electrophile. So that's going to collapse down. And so if we count 3, 4, 5, 6, 7, that's going to form a 5-membered ring. Now the first thing we want to do is just draw a 5-membered ring. Now we're going to use those blue numbers and put those in first. 3, 4, 5, 6, 7. So 4, 5, and 6 stay CH2s. 3 has one H coming off it, and then it has the methyl ketone. Seven got attacked, so it's going to have its methyl group coming off at 8, and then the oxygen O-. Then you can go back and just put your numbering in. So we're forming a bond between 3 and 7. And now we have this O minus. So we're going to do a proton transfer with water. That's going to get us to our beta hydroxy ketone. So overall, we're ending up with a 5-membered ring. Any questions on that? So I'll have a little bit more to say about this at the end of the lecture when we get back into this concept of dehydration across the alpha-beta bond. Remember, we talked about that a little bit in the self aldol when the H from the alpha carbon and the OH from the beta carbon can be eliminated to form a double bond. So here is that slide, and basically, as we said, because your alpha carbons are different, you need to predict the ring size and then go with one that's reasonable. Another thing that can guide you is under these conditions, it's the more substituted enolate or the thermodynamic enolate that was used versus the kinetic. And because the mechanism's reversible, even if you did deprotonate from carbons 1 or 8, those products could get funneled back in to starting materials to go from the other side. And so in moving up the chain from alkylation to aldol, the last reaction that we're going to study here is the Claisen reaction. And so it can be just like the aldol where there's self-Claisen or cross-Claisen. The example that we're seeing here is using ethyl acetate. So that's an ester. So remember, there's the alpha carbon of the ester. It's going to react with a molecule of itself, which I'll draw over here. So if this is the enolate, then this will be the electrophile. And so that carbon of the electrophile becomes the beta carbon. So you're making, again, C alpha, C beta. Notice in the electrophile that this thing is now gone. So the enolate attacks, it goes through mechanisms we've seen before in the prior modules. So essentially what it is a nucleophilic acyl substitution. So since the beta carbon, so beta carbon is sp2, you can no longer form stereocenters there. So the only stereocenters you can get are at the alpha carbon if there's appropriate substitution. And so this product is typically called a beta keto ester. And now it has reactivity that's completely unique to it now. And that's the basis for a couple reactions that we'll see today. So let's just draw the mechanism here. We're going to take ethyl acetate, so a couple things I do want to point out. Typically in these reactions, we're not dealing with strong bases. So notice the base is sodium ethoxide. It's run in ethanol. So the pK of that is about 16. The pK of your ester is about 20, 21, something like that. So you're essentially under equilibrium conditions to a certain point in this mechanism. And it says then H3O plus. So these reactions require an adjustment of the pH to below 4. The other thing I want to mention, whatever ester you start with, see how this is O-ethyl? That has to be the same as the solvent and that base that you're using. So that stuff needs to be matched. So we'll form our ester enolate. So there's the ester enolate, that's the nucleophile. This will collapse down. It will attack that carbonyl. So that's your nucleophilic addition part. So at that point, the carbon becomes sp3 hybridized. It's gone down in oxidation state because now it looks more like an acetal. And what's going to happen is that this will collapse and then eliminate off that good leaving group, ethoxide, which is the base that you're using anyway. And so this is the weird part of this mechanism, because it looks like you've formed your product, but you have and you have not, because once you form this beta keto ester, the acidity of these hydrogens is now a pK of 10, and that ethoxide that you just formed is going to act as a base, which is going to irreversibly deprotonate them. So at this point, it's no longer these equilibrium arrows. It's a one-way street. So the reaction will stop there until the pH is adjusted. which essentially means you're dribbling in hydronium of some sort. And really, it's an acid-base reaction, so that enolate gets protonated, and you end up with the neutral compound. Again, the important thing to, as I'll highlight, it's this arrow that I highlighted in blue here. That's the driving force for the reaction. That essentially gets it out of all those prior equilibrium steps. So the formation of that beta ketoester, what's important is that those alpha hydrogens are now pretty acidic. So they're at a pK of 10, and so they're really easy to substitute. So you can deprotonate them, they can undergo alkylation, aldol, all that sort of thing pretty easily. So here's that product, and it says it's the self-Claisen product. So one thing you need to be able to do is look at something and say, yes, it came from these starting materials. Again, what's hard about this one is like this whole group here, you know, if you think of that as sort of the X group, so the ethyl acetate has undergone a nucleophilic acyl substitution of that O-ethyl for that entire group that's in that box. That's one way to think about it. And so now this compound has two different alpha carbons, and they both have very different acidities. So alpha, you know, that pK can be anywhere from, say, 20 to 25, but alpha prime is about 10. So that's a huge difference, you know, 10 to the 10, meaning you can specifically act upon those alpha prime hydrogens in preference to the alpha. So these CH2 or methylene are much more acidic now. So what can be complicating for this, but a reason why they're so much more acidic, is you can delocalize that negative charge a couple different ways, either into the ester carbonyl or the ketone carbonyl. And again, anytime you can delocalize that negative charge, it stabilizes it. So those H's are, because they're more acidic, you can use a much weaker base to deprotonate them. And again, that's typically, as I'll highlight in blue, you want to match whatever the alcohol of that ester is to that base in that solvent. So those things should be matched. So to show you, extending the aldol logic to Claisen, if you were to do a crossed Claisen, you're still going to end up with a mixture of things, but not as bad, because remember that beta carbon is no longer a stereogenic carbon. So as you can see in the two columns, the self so this alpha carbon here is a stereocenter now. And then in across, that alpha carbon. So total, you're not getting as many products because that beta carbon is sp2 hybridized. So just as with the aldol, one way you can control the is if you use non-enolizable esters. So these have to be the electrophiles. Meaning that the carbonyl will end up as the beta carbon in the product. So as you see in each of these ethyl formate, there's no alpha carbon. Ethyl pivalate, the alpha carbon's blocked. There's no acidic hydrogens. Ethyl benzoate, it's sp2 hybridized. And then diethyl carbonate, you're at an oxidation state of 4. So you're going to do a nucleophilic acyl substitution, and that's going to be what's installing your ester component. And we'll see an example of that in the slides coming up. So just as with the intramolecular aldol, the intramolecular Claisen has its own name. It's called the Dieckmann cyclization. So a Dieckmann reaction it's going to give you the beta keto ester that's embedded in a ring. And because you're starting with an ester, we don't have this issue of so many alpha carbons. So here your alpha carbons are at 2 and 5. Given the symmetry of the molecule, it doesn't matter which one is deprotonated. So we say alpha. If we deprotonate at 2, it's going to attack carbon 6. So 1, 2, 3, 4, 5. That's going to get you a 5-membered ring. And so without, going through the whole mechanism, because we know from that analysis, we're going to form a 5-membered ring. We can say, okay, carbon 2 is going to attack carbon 6. And nothing happens at 3, 4, and 5, so we just fill those in. So if we're starting at 2 and we're attacking 6, 6 has to end up being the ketone. So that's the beta keto part, and then at carbon 2 is our ester. if you do the analysis the other way, you have carbon 5 attack carbon 1, you're going to end up with the same product. But most of all, when you're figuring this stuff out, you want to do that sort of analysis to predict your ring size and then put your substituents in. So mechanism, I don't think we need to do that. So this reaction here is special because we're going to use that oxidation state 4 electrophile to install the ester part of the beta keto ester. And so again, that electrophile was diethyl carbonate. And from cyclohexanone, if we treat with LDA, THF, that generates the ketone enolate. That's going to attack that electrophile. And then ultimately, in terms of your oxidation states, this reaction is installing the ester part of the beta keto ester. So just as a connection to the prior slide, if we wanted to make that from a Dieckmann, this would be the bond that we have to break. And then we would just shove an ester functionality at the beta position. So I'll try to keep things sort of the same. I'll have a really weird looking bond here. So I just drew it to sort of get past that, but that would be something you could use to make that product that's shown in the prior reaction as well. So that gives you some leeway in terms of what you can start with, practically speaking, like what's commercially available. Probably the issue with doing a Dieckmann here is, again, since you're making a bigger ring size, that carbon chain is really long and floppy, and only a certain amount of time is it the nucleophile and electrophile are going to come around together to react. What you're fighting as well is not only you want the intramolecular cyclization to happen, but you can also get an enolate from one chain attacking an ester from another, and now you're sort of dimerizing, and you don't want that to happen. So now that we know how to make beta keto esters, and we know that the alpha carbon sandwiched between the two carbonyls has increased acidity, there's two classic reactions in this chapter. So acetoacetic acid and malonic ester syntheses. So the first one makes a substituted acetone, and the second one makes a substituted acetic acid. And what do I mean by that? So this molecule is acetone. This molecule is acetic acid. So you're looking for those patterns. And if the acetone is substituted, say there's an R group. Or if the acetic acid is substituted, there's an R group. So you're looking for those patterns. That's going to tell you what's alpha and what's beta, how you can combine those using the chemistry we've seen. So at this point, it's really about pattern recognition and the strategy. So the starting material for the acetoacetic acid is the self-Claisen product that we saw already. And we're going to take that, treat it with sodium ethoxide and ethanol. If you're curious, I'm sure you've seen booze, but have you ever seen like pure ethanol? I mean, pure ethanol looks like water. It smells a little sweet. To make sodium ethoxide, all you're doing is throwing in little chunks of sodium. The sodium will off-gas, it'll eventually dissolve, and that's how you get sodium ethoxide in ethanol. It'll still look translucent, but it might take on a little cloudiness. But that's generating the base. That base is then going to deprotonate from the alpha position to generate the enolate. And then as we saw in the beginning of this module, the enolate can react with an electrophile. You know, this is like your standard SN2 type electrophile. And that'll substitute an H for R1. And so if you look at that, what's buried in that structure is this. However, we still have this stuff in there. So once you get to that point, two more things need to happen that are shown on the next slide. We have to get rid of that carbon at the oxidation state 3. So from reactions that we've already seen, this group is essentially burned off. So again, that's oxidation state 3. When we treat under basic conditions, that takes the ester to the acid. That was called saponification. And at that point, since it's still the carboxylate salt, the pH is adjusted with HCl, and then the temperature is raised quite a bit. And so essentially what that is going to do is extrude CO2 gas to generate the substituted acetone. So there's two components here. The 3 carbon unit, that's a ketone, and then that R1. And so the bond that we're really concerned about making is that between the alpha and the beta carbons. So on the next slide, if you're wondering like how does this happen, so we'll draw that mechanism. So I'm going to draw the beta keto acid it's already been protonated, so we added in the HCl. And at this point, the molecule is going to adopt this confirmation. So it has to be this because that's how this transpires. So this is our beta keto acid. And then again with high heat, this pi bond is going to abstract that H. We're going to break the OH bond to form C double bond O. And then what's weird here now is we're breaking a bond to an sp2 hybridized carbon. So that goes like that. Normally we've not seen anything like that before. But what results in that is the formation of an enol in CO2 gas. So the enol will undergo a tautomerization. And again, that's just a 1, in this case, a 1,3 H shift. The CO2 gas again bubbles out. So this is our substituted acetone. So given this molecule, hexane 2-one, what electrophile was used in its synthesis? If we're going to employ the acetoacetic acid synthesis, what electrophile was used? So if we use the highlighter, here's the 3. Make sure I get my colors consistent. Here's the 3 carbons from the ketone. And then everything else from the beta carbon on came from the electrophile. So this is the bond. So there's alpha, there's beta. So we know that the beta carbon has to have the leaving group. So to get to the right answer, it's C1 bromopropane. So alpha is always the enolate, B is always the electrophile, and then at that point, since you know you're making that bond, you're just counting carbons. So if we ratchet it up a little bit, imagine since you're starting with ethyl acetoacetate, which has 2 hydrogens, you can substitute both of them. And so again, if we just highlight, so there's the 3 carbon atoms, there's the ketone. So there's your alpha. In terms of your electrophile now, it's again everything else. So there's 4 carbons. And you've done the substitution twice. So we're using, I think, iodine here. So you could do that. substitute both of those H's to make a ring. So 1,4-diiodobutane. So that's to make substituted acetones. You can also make substituted acetic acids. And notice now what you're starting with is called diethyl malonate. So those carbons are both at oxidation state 3. We can form the enolate. We do an alkylation with R1X. So that gets us our H for R1 substitution. And then it's the same thing as before: saponification, acidification, decarboxylation. Any other ation you want to throw in there. So again, this all happens pretty much in one flask. You're running it first under basic conditions, and then at some point, through thin layer chromatography, you're saying, okay, the diester is now been converted, so now I'm going to adjust the pH and run it under acidic conditions, and then heat the crap out of it and generate the acetic acid. So really, you're just looking for a carboxylic acid. And anywhere you see, substitution from alpha to a beta carbon, you can use this reaction to make that. So diethyl malonate is like dirt cheap. I think I have like 5-gallon bucket of it in my lab. I mean, you can get it for like $15 for a 5-gallon bucket. So it's nice because if you're feeling bad, you just run one of these, it's guaranteed to work. Then you can say, yes, I know what I'm doing. So if you wanted to make 3-phenylpropanoic acid, what electrophile would you use to make that? So there's alpha, there's beta. So that's the bond we want to basically slice or make, depending on how you're thinking about it. Just through visual inspection, we can eliminate B and D because there's no aromatic ring. C would be out because that's sp2 hybridized. And again, the alkylation step is SN2. So it needs to be sp3. So this ends up being your beta carbon. So A would be the correct response. Any questions at this point? So now that we've seen these 3 different types of reactions, looking at the beta carbon, specifically its oxidation state, is it 0, 1, or 2? We're going to circle back and catch up with this sort of side path of the aldol dehydration product. So remember that the aldol product, it has the alcohol at the beta carbon. When it undergoes dehydration, it's losing the elements of H2O across the alpha and the beta carbons. So now you have this dehydration product, And so that's an unsaturated aldehyde, so it's called an enal. So an alkene, aldehyde, enal. And what is interesting about these is they undergo a unique sort of reaction. So again, these are made through the aldol dehydration, and now they can then be treated with nucleophiles to form a different type of bond. And one way to understand what's happening is using resonance hybrids. So we know that carbonyl oxygen's delta minus, carbon's delta plus. If you show that formally through resonance, the oxygen's minus, that carbon's plus, and then see this bond, how it migrates over. It puts that plus charge that was at the beta carbon. And then this then looks like an enolate, right? So those arrows coming down, putting a negative charge there. So what it's telling us is that formally a way to think about the double bond is through this sort of polarity. We know that negatively charged things, nucleophiles, are attracted to positive. This negative is attracted to an electrophile, so you can think of nucleophiles adding to the beta carbon, and then the subsequent enolate attacking an electrophile at the alpha carbon. And this is a strategy that chemists will use to functionalize the alpha and the beta positions. So why is that powerful? Well, if everything's different, then you've generated two stereo centers. And if you're able to control that, you can make some pretty complex things. So what is this telling us? The beta carbon is electrophilic. So if you think about, we just learned how to generate enolates. You can get an enolate to attack that position. And then you can either protonate the alpha position or treat it with another electrophile. And so this reaction is called the Michael addition. So that's another famous one that, coming out of this class, you should know what a Michael addition is. I'm recording this, so I have evidence that I did tell you what it is. But again, the Michael addition is really well studied. We talked about David McMillan winning the Nobel Prize, and he was able to generalize organocatalysis to Michael additions. And I mean, you can do virtually anything now with organocatalysis. That was, I would say in prior years, you had to have a little bit more training in terms of how to handle things, but the organocatalysis makes it accessible to pretty much everyone. So here's an example of that. So the diethylmalonate is going to be the nucleophile. The enal will be the electrophile. And what's going to happen now is the enolate adds to the beta carbon. So now you're actually forming a carbon beta, carbon gamma bond. So I'll highlight that in red here, or blue, sorry. So you're forming that bond. and notice that the alpha carbon gets protonated through the reaction. So generally for a Michael addition, these are the nucleophiles that are used. Potassium cyanide, enolates, amines, alcohols, or thiols. Because they're weak nucleophiles, the reverse process, the retro-Michael, can happen as well. That's where you just deprotonate and then eliminate to reform the starting alkene. So the species that have the double bond are called Michael acceptors. So what is the common theme here? You have a double bond, and then to that is an electron withdrawing group. So I'll highlight those in blue. Stupid pens, man. I'm gonna break this iPad in half. Okay, so blue. So the aldehyde, the ketone, the acid, ester, nitrile, and nitro. So it has to be an electron withdrawing group so that the beta carbon gets attacked by the nucleophile. I think it's ethyl acrylate. I think that's like in super glue. So the way that works, like why super glue, like if you get it on your finger, like why it works so fast. So we'll just use like water as the initiator. So pretend there's like, there's just the moisture of water on your finger. So if that does a Michael addition, you form that, and then that's going to react with another monomer of ethyl acrylate. And then that's going to react with another one. So eventually, you get this monomer or this polymer, and then your fingers are glued together. So what I showed was the anionic polymerization. You can also use radical initiators for this, for any polymer students. This is like old school, like polymerization. Nowadays, they have these things called like raft. Forget what that stands for, but you can start with these initiators that decompose. They kick off the polymerization, and then part of that initiator comes back and gets trapped. So the initiators and the monomers are pretty well sophisticated now based on sort of this earlier understanding of mechanisms. So which of the following is not a Michael acceptor? So they all have alkenes, but when you look at what's bonded to them, A is the only one that does not have an electron withdrawing group. So really, in terms of the pattern recognition, say here's your alkene, 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 and then that blue part is the electron withdrawing group. So the OH would be an electron donating group into that alkene in terms of the reactivity. And so I think what we'll finish today off on is a reaction that's called the Robinson annulation. But really what it is a Michael addition followed by an aldol reaction followed by a dehydration. And so if you look at what we're starting with and what we're ending up with, I'll do some highlighting here. So there's where the carbons are going. And the product is always a 6-membered ring. So you have an existing 6-membered ring and you're making one. So the step, okay, so the first thing that happens is a Michael addition. The second thing that happens is an intramolecular aldol. And then the last thing that happens is a dehydration. So when you're looking at the product, what can get sort of confusing is just spotting how things map onto each other or the sequence in which things happen. So you see here alpha, alpha, beta, and it's a double bond. So what that's telling you is right there, that's where the aldol dehydration occurred. And then on the other side, this is where the Michael addition occurred. So you're forming that beta gamma bond. So don't get confused about, the Michael and the aldol, what's forming what. But we'll run through this mechanism real quick. So first thing we want to do, there are many alpha carbons in this molecule, but only the most acidic one is going to go first. So it's going to be that one because it has a pK of about 10. So we're going to form that enolate. These other alpha carbons, so here, or there, again, they're going to have pKs that are much higher. So the most acidic one goes first. That forms the enolate. That enolate is then going to do the Michael addition. So again, that's the addition of the nucleophile to the beta carbon. So I'm going to show it as that carbanion. So we need to protonate that. And that's messy. Let me erase that. So that gets protonated. That's the Michael product. Now again, we have many alpha carbons here. So alpha, alpha, alpha prime, alpha double prime. If you ask yourself, okay, which one gets enolized, which one attacks a carbonyl? The only reasonable one is this alpha double prime. So if I put some numbers in blue and count, so 1, 2, 3, 4, 5, 6. So that would make a 6-membered ring. If I say alpha prime, that would be 3 to 6, so 1, 2, 3. That would make a four-membered ring. So 4-membered ring would be 2 strained. A 6-membered ring is just right. Alpha, this alpha to that carbonyl isn't going to be preferred because it's going to generate a weird, ultimately, it'll generate another ring, but I think it's going to be too strained in terms of how the enolate could attack that carbonyl. So we're going to generate the enolate starting at alpha double prime here. So I'll just draw what that enolate is. So now that is the aldol reaction. So that was a 6-membered ring adding on to a 6-membered ring. So there's alpha, there's beta, and at that point, the OH gets, or the O minus gets protonated, and then you dehydrate across that alpha beta bond. So OH, H, and then again, the final product, you're able to spot the aldol dehydration because that's where the double bond is. Pretty quick. So I think you can go through these. So you can see how to spot things. So if we wanted to make that product shown, what would be the donor and the acceptor? So there's that. Because it's between alpha and beta, that beta carbon has to have a carbonyl. And really C is the only one that has that carbonyl. So those 4 carbons have to come from that as the Michael acceptor. Remaining so here's an interesting one. I think this was taken straight from the ACS study guide at some point along the years. So you have an alpha beta, or excuse me, you have a 1,3 dicarbonyl or a beta diketone. What starting material would make that? A, B, C, or D? So if we look at it that way, that beta carbon is at oxidation state 2. So in the starting material, it has to be at oxidation state 3. So that's going to eliminate A, B, then you're left with C and D. So C is the only one that's going to get you the right carbon count and things in the right places. So it's essentially a ketone enolate reacting with a non-enolizable ester in a variant of the Dieckmann cyclization. Slides were just questions. So I think we have one more here. This is definitely from the ACS study guide. So we have acids A, B, C, and D. Which acid can you blow off as carbon dioxide through decarboxylation? So the only one that is sort of unique is D, because it has a ketone at the beta position. A, B, and C do not. So to do decarboxylation, you have to have a beta keto acid. If you don't have it, then you can't do that method. So the winner here is going to be D. So that's going to wrap it up for today. You do have a quiz.